Next, I want to take a few minutes to talk about the famous Adabus theorem and what its practical implications are, which are extremely interesting. So, if you remember, the way that boosting came about is that Kearns and Valiant had this famous question, can you combine weak classifiers to make a stronger one? Actually, Valiant is a Turing Award winner, so really famous professor from Harvard. And Shapiri, a couple of years later, came up with the idea of boosting, which really changed the machine learning field. And so, if we look at the iterations of boosting in the x-axis here and the training error for a toy data set, we observe a very practical effect that we see in a lot of boosting data. We're going to start with a really bad training error. So our first decision stump has training error of 22.5%. So not good at all. After 30 iterations, as we saw a little earlier, we're going to get all the data points right in our training data. And I showed you kind of that crazy decision boundary for this. So we see a smooth transition, iteration after iteration, where the classification error tends to go down, not always exactly, but tends to go down, and eventually goes to 0, and actually stays at 0. And that's a key insight of the boosting theorem. So here is the famous Adabus theorem, which underlines all the choices we made in the algorithm and really has had a lot of impact in machine learning. Basically, the theorem says, under some technical conditions, and all theorems are like this. Now, if you were on TV, you would say, some restrictions apply, see stars for details. So you say, under some technical conditions, the training error of the classifier goes to 0 as the number of iterations of the number of ensembles that we consider capital T goes to infinity. So, in other words, pictorially, we'll see that we expect the training error, which is this thing here on the y-axis, to go eventually to 0. Now, that's eventually. It might oscillate a little bit in the middle. However, what the theorem says is that it tends to generally decrease, eventually become 0, usually, and then stick at 0. So you're going to see this high in the beginning, wiggle, 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 but tends to go down and then hit a certain value, usually 0, and sticks at 0. Now, let me just take a minute to talk about those technical conditions and start with details. It turns out the technical condition is something quite important. It says that at every iteration t, we can find a weak learner, so a decision stump that has weighted error at least a little bit lower than 0.5. So it does at least better than random. That's what the theorem says. It seems like intuitively you should always find a classifier that does better than random, even on weighted data, but it turns out that this is not always possible. So here's like a counterexample, which is a really extreme counterexample, but there's other examples where it's not possible. So for example, if you have a negative point here and you have a positive point on top of it, there's never going to be a decision stump that can separate the positive point on top of the negative point. So the conditions of boosting algorithm might not be satisfied of the Adabus theorem. However, nevertheless, boosting usually takes your training error to 0 or somewhere quite low if the number of iterations go to infinity. So we do observe that decrease in practice, although there's some technical conditions in the theorem, so it might not go exactly to 0, but it can get really, really low.